In this video, we will look at exercise 13 from the 1.1 Vectors handout. Two ropes are used to suspend an 80-pound object from the ceiling. Notice here that we have pounds, which is a unit of measurement of force and not mass. So we do not need to introduce the acceleration due to gravity, 9.8 meters per second squared, or 32 feet per second squared, in order to get force. We are using two ropes to suspend this object, and so one of them is suspended with an angle of depression of 60 degrees from the ceiling, while the other has an angle of depression of 30 degrees, and the magnitudes of tensions are called T1 and T2. Let's sketch this so that we can see all of the vectors and come up with the components from the problem. So we have an object which is being suspended. Ideally, you might put the object here, but I'm going to use a vector acting straight down in a free body diagram, and I'm going to call this the weight vector, or the force due to gravity vector. Now I know this force has a magnitude of 80 pounds, and it's acting in a direction of 270 degrees. So I'm going to write that in polar form right away. Then I'm using two different ropes. I'll give them two different colors. One has an angle of depression of 60 degrees, so if we imagine a ceiling here, the angle of depression of 60 degrees is going to be like this, which by the alternate angle theorem in geometry gives us the same angle of inclination. And so I'm going to keep those angles in there, but I'm going to write the tension 1 vector with its unknown magnitude T1, measured in pounds, and the direction in standard position from the horizontal positive side of the x-axis is 60 degrees. We have a second magnitude measured from the ceiling, or a second force measured from the ceiling, second angle, and that angle is going to be 30 degrees. And we still have a reference angle here of 30 degrees, but of course we need to come up with the angle in standard position, which is going to be 150 degrees. So we have our tension 2 vector in partly polar component form with a magnitude of T2 and a direction of 150 degrees. Because we are going to be getting the resultant vector or adding these vectors together, we need to have the vectors in rectangular form. So I'm going to relist these vectors in rectangular form. So we have T1 times the cosine of 60 degrees number of I hats. Well, let's do it this way first. I'll use the rectangular brackets, and then after I work out the sine and the cosines, I will write it in I hat, j hat notation. The cosine of 60 degrees is 1/2, and so we get 1/2 T1, number of I hats. And then the sine of 60 degrees is the square root of 3 over 2 multiplied by T1, number of j hats. The green vector, the T2 vector, similarly has T2 cosine of 150 degrees for its horizontal component and T2 sine of 150 degrees. I will ask you to pause the video, complete listing out all of these vectors, and then resume the video in a moment to compare and see what the next step or the concept is to solve the problem. Now that we have all of our vectors listed to the best of our ability, we need to think about what's going on with the concept here. If these ropes are doing their job, this object is not going to be moving. But the fact of the matter is it's not moving to begin with, and so we are not changing its motion or its velocity. And because the change of velocity is equal to 0, because it's initially at rest and continuing to stay suspended or at rest, the change of velocity is 0, and over time the change of velocity is still 0, and therefore we have that the acceleration is equal to 0. Therefore, by Newton's second law, which says that the net force is equal to the mass multiplied by the net acceleration, and the net acceleration is equal to 0, we know that the net force must be equal to 0. And so this is the equation that we will use to solve for our two unknowns. But if you recall from algebra, if we have two unknowns, we need more than one equation to solve for both unknowns exactly. In fact, we need two equations. But indeed, that's what this vector equation is telling us. Because we are in two dimensions, we have an equation 1 for the x components, and we have equation 2 for the y components. So I invite you to pause the video, set up these equations, and solve for the T1 and T2 unknown magnitudes, and then resume the video to compare your answers with mine. So here we have a reminder of the concept of Newton's second law and the fact that the net acceleration is zero. We have that the sum of all of the forces must be equal to the zero vector. The zero vector is this 0 I hat plus 0 j hat vector. Now that we're adding all three vectors together to get 0, I've broken it into the different colors, the T1 vector, the T2 vector, and the weight vector of the object. Therefore, we can take all of the x component coefficients, the I hat coefficients, and come up with a scalar equation. And when we multiply by 2 and isolate T1, we see that T1, the magnitude of the tension 1 vector, is square root of 3 multiplied by the magnitude of the tension 2 vector. Let's put this in a box, call it equation 1, and hold on to it for a moment. Then we extract all of the y component equations. I'll just highlight those in case you didn't see them the first time around. All of the j hat coefficients, we extract these numbers and make the second equation over here. And when we do a little bit of algebra to rearrange and simplify, we can multiply both sides by 2 and take the constant term to the other side so that we get the square root of 3t1 plus t2 is equal to 160. I put a box around that and call it equation 2. Now it's just an algebra equation for equations 1 and 2, and we can substitute t1 in equation 1, and I'll put a green box around that t1, and I'm going to use this expression and substitute it in here. So I get the square root of 3 multiplied by the square root of 3, which is 3, and that's times t2. So this first term gives me 3t2 plus 1t2, which is 4t2, is equal to 160, and therefore 160 divided by 4 gives me 40 pounds. When I take that 40 pounds and I substitute it back into equation 1, I say root 3 multiplied by 40 pounds gives me 40 root 3 pounds. And therefore we have solved for the two different magnitudes of the two different tension vectors.